Hello learners, this is Habeeba with Excelwithme. If you like the video, please do like, share, subscribe and comment below. Let's start today's class, that is research methodology topic, tests of significance, non-parametric tests and data analysis. Already we have done the two subtopics of this, and then we are going to do the third topic, that is non-parametric tests, chi-square test, median test, Mann Whitney test and Kolmogorov two sample test. Now, sampling and sampling distributions of quantitative analysis for managerial decisions introduced to the general class of testing of hypothesis. These tests, popularly known as parametric tests, assume that parameters such as mean, standard deviation, etc. exist and are used to develop a test. These are, we have to note down, these are the parametric tests here. That is mean, standard deviation, etc. whatever we calculate. For example, a t-test is based upon the comparison of means of two samples. The parametric tests are developed with an assumption that the form of the population distribution was known and that a test concerning a parameter of the distribution was to be made. Now, tests of hypothesis which deal with the population parameters are called parametric tests. Now, what are non-parametric tests? There are situations, particularly in psychological research studies, where in the basic assumptions underlying the parametric tests are not valid and one does not have the knowledge of the distribution of the population parameter being tested. For example, when we do the t-test in parametric tests, what happens? Already we have, suppose we have taken the two subjects, we are seeing whether any difference is there in the achievement of the students. We take the means of it and we calculate them, take the standard deviation, and we see the t-test, and when we will decide whether there is a relationship or not, is there or not. The tests which handle problems of these types are when we don't understand, when the distribution of the population parameters we are not able to understand, then what happens? These tests which handle problems of these types are known as non-parametric tests or distribution-free tests. In the recent past, the non-parametric tests have gained importance basically for three reasons. Number one, these tests require no or less restricting assumptions than the corresponding parametric tests. In parametric tests, we have assumptions there. Now, these tests are, second one, these tests are more suitable for analyzing ranked, scaled or rated data. And the third one is these tests involve very few arithmetic computations. Now, the following are some of the typical situations for using non-parametric tests here. Sometimes the responses to a question are given in terms of names, that is nominal data, which cannot be treated as numbers, male, female, like that. Now, for example, if we ask your young graduates in which part of the country would you like to take up a job and live, the replies could be north, northwest, west or south, etc. Now, nominal data can be analyzed only by non-parametric methods. In mailed questionnaire method of survey, more often partially filled questionnaires are received. Now, non-parametric tests are designed to take the mission's data and make necessary adjustments to extract maximum information from the available data. Now, non-parametric tests can be used to provide reasonably good results even for very small samples. Now, one sample test. What are one sample tests? The one sample tests are used to answer the questions such as, is there a significant difference between the observed and expected frequencies? Is it reasonable to believe that the sample has been drawn from a specified population? Is it reasonable to accept that the sample is a random sample from some known population? The tests which are used to obtain answers to the above questions are classified as tests for goodness of fit. Now, chi-square test. The chi-square test is used for comparing experimentally obtained results with those to be expected. The important application of chi-square is as given below. Number one, chi-square as a test of goodness of fit. Chi-square goodness of fit test is used to find out how the observed value of a given phenomena is significantly different from the expected value, whatever value we are expecting. In chi-square goodness of fit test, the term goodness of fit is used in order to compare the observed sample distribution with the expected probability distribution. Now, chi-square goodness of fit test determines how well theoretical distributions such as nominal, binomial or Poisson fits the empirical distribution. In chi-square goodness of fit test, sample data is divided into intervals. Then the numbers of points that fall into the interval are compared with the expected numbers of points in each interval. Now, in regard to the procedure, set up the hypothesis for chi-square goodness of fit test, that is set up to both null and alternative hypothesis. A null hypothesis in chi-square goodness of fit test. The null hypothesis assumes that there is no significant difference between the observed and the expected value. We have to remember, this is very important point. There is no significant difference between the observed and the expected value. Now, what is exactly opposite to that alternative hypothesis? In chi-square goodness of fit test, the alternative hypothesis assumes that there is a significant difference between the observed and the expected value. Now, calculate chi-square using the formula and find out for the given degrees of freedom if chi-square value is significant at 0.05 or 0.01 levels. If so rejected, the null hypothesis. If not significant, accept the null hypothesis. Number 2, testing hypothesis of equal probability. That is, the chi-square test is a useful method of comparing experimentally obtained results with those to be expected theoretically on some hypothesis. The formula is given here down. You can pause and note down, where FO, that is observed frequency of a phenomena or even which the experimenter is studying, FE, that is expected frequency of the same phenomena based on no difference or null hypothesis, observed and expected. The use of the above formula can be illustrated by the following example here. An attitude scale designed to measure attitude toward co-education was administered on 240 students. Now listen carefully, very important example here, you will understand very easily if you carefully listen to it. They have to give their response in terms of favorable, neutral, unfavorable. Of the members in the group, 70 marked favorable, 50 neutral and 120 disagreed. Now, do these results indicate significant difference in attitude? The observed data is FO given in the first row of the table I'll show you just now. In the second row is the distribution of answers to be expected on the basis of null hypothesis FE if each answer is selected equally. You can see the table here, responses from the subjects in regard to the attitudes. Now FO, FE given here, favorable FO, that is observed is 70 and the expected is 80, neutral 50, expected 80, unfavorable 120 and expected is 80, that is 240 students observed and expected. Now all the calculations are done here. The formula also chi-square is answer with 32.5 and degree of freedom that is equal to 2. Now entering table of chi-square which can be obtained from any book of statistics, we find in row that is degree of freedom is equal to 2, a value 5.59 and 9.19 given under the heading that is 0.05 and 0.01 levels of significance respectively. Now our obtained value is 32.5. You can see here in the previous one we got it as, sorry, here we got it as 32.5. So, which is far above the given value in the table, thus our results will be marked significant at the 0.01 level. Now, we discard the null hypothesis which stated that there will be no difference in the attitude, but from the results it may be stated quite confidently that there is difference in the attitudes of people towards co-education. It may also be mentioned that these results clearly indicate that the results are not due to any chance factor. So easily we can understand here. Now steps for chi-square testing, let's see here. First, set a null hypothesis, collect the data and find out observed frequencies, find out the expected frequencies by adding all the observed frequencies divided by number of categories. In example 1, that is 240 divided by 3 equal to 80. In second example, 100 divided by 5 equal to 20. Find out the difference between observed frequencies and expected frequencies, that is FO minus FE. Find out the square of the difference between observed and expected frequency, FO minus FE whole square, divided by expected frequency. Again, you will get a quotient. Find out the sum of these quotients, determine the degree of freedom and find out the critical value of chi-square from table. Generally tables are given to find out the critical values. Compare the calculated and table value of chi-square and use the following decision rule. Now accept the null hypothesis if chi-square is less than critical value given in table. Then reject the null hypothesis if calculated value of chi-square is more than what is given in the table under 0.05 or 0.01 significance levels. Now let's understand the median test. Now it can be said that median test is a non-parametric alternative of t-test. It can be employed to know if the median of a certain data is same as that of assumed median, in which case one sample median test can be used. It can also be used to know whether two or more samples that are independent and equal or not equal with regard to their size have different median or not. Thus, medians of two sample subgroups are compared and these samples can be equal or unequal in size. Now, median test is a non-parametric test, statistic, and thus it can be used with distribution that is normal or not normal. Further, it can be used with variables having either continuous and discontinuous measurements. It can also be conveniently used with some small sample, though when compared with Mann Whitney U-test, it is less powerful. Now, we need to remember that the assumptions of non-parametric tests are applicable here as well. Let us now look at the assumptions of median test here. Number 1, the scores in the samples 2 or more can be measured in terms of ordinal scale of measurement. 2, every score in the sample occurs in a random manner. 3, every score is independent of other scores. 4, the samples 2 or more need to be independent and not correlated to each other. Now, computation of one sample median test. Let's see here. One sample median test is used in order to know if the median of certain sample is equal to population median that is assumed here. Let us now try to understand the computation of one sample median test with the help of steps here. Also, some values are given. A psychologist wanted to know the average years of experience of newly appointed junior lecturers in the organization. The data collected is given as follows: 2, 3, 6, 4, 3. You can see here the data. Step 1, null hypothesis is to be formulated here, that is H0. The median years of experience of junior lecturers will be the same as the assumed median years of experience. Then step 2, assuming median sample years of experience as 5. Step 3, coding the scores. The scores having lower value than the assumed median are to be given the codes as 0 and the scores having value more than assumed median. Those having value more than the assumed median will be given as code as 1. The values that are the same as that of the assumed median will not be considered. Now here you can see the coding is done. 2, that is 0, 3, that is 0. How I told you just now, more than the number of 5 that will be given as 1, below 5 that is 0 are coded here. Now step 4, rearranging the data. The data is now arranged in terms of frequency of scores above assumed median and below assumed median, as can be seen below. Above assumed median is 6, below assumed median is 8. Now step 5, frequency expected, that is FE, is computed using the formula here, n equal to 14, that is the total number of participants. FE, that is 1 by 2 into n, that is 7. Expected is 7. Thus, frequency observed FO, that is 6 and 8, frequency expected is 7, 7. Now step 6, chi-square is computed using the following formula here. Answer we got 0.28. Now step 7, interpretation. In order to interpret the obtained chi-square, we need to first know the degree of freedom that will be. What is the degree of freedom here? R minus 1, K minus 1, first and second one. R means rows, K means columns. Thus 2 minus 1, here we got degree of freedom 1. Thus degree of freedom is 1. Now we can refer to the chi-square table that is given in already in the given of any, I'll show you, of any statistics books. You can see the critical value of chi-square for DF equal to 1 is 6.635 at 0.01 level of significance and 3.841 at 0.05 level of significance. The chi-square obtained by us is 0.28, which is lower than the table value at both the levels. Thus, the null hypothesis accepted. If we get more than the table value, then we have to reject. Here, we need not, because it is less than the table value here. So, we accept. And it can be said that there is no significant difference between the assumed median and the sample median years of experience of the newly appointed junior lecturers. Now, Mann Whitney test. When we are interested in testing of difference in means of two independent populations, then we use two sample t-test. To use the t-test, however, it is necessary to make a set of assumptions. In particular, it is necessary that two independent samples be randomly drawn from normal populations having equal variances and the data be measured in at least of an interval scale. But in studies of behavior, research, experiment of psychology, etc., generally the data are collected in ordinal scale and the form of the population is not known. Since the parametric t-test could not be used in such situation, an appropriate non-parametric technique is needed. In such a circumstance, parametric test known as Mann Whitney U-test may be used. This test was developed jointly by Mann and Whitney and Wilcoxon. Wilcoxon considered only the case of equal sample sizes, while Mann and Whitney seem to have been the first to treat case of unequal sample sizes. Therefore, it is sometimes called the Mann Whitney U test and sometimes the Wilcoxon ranks sum test. Thus, this test may also be viewed as a substitute for the parametric t-test for the difference between two population means. When assumptions of the two sample t-tests are fulfilled, then this test is slightly weaker than t-test. Now, what are the assumptions? This test work under the following assumptions. Number 1, the two samples are randomly and independently drawn from their respective populations. Second, the variable under study is continuous. Third, the measurement scale is at least ordinal. Fourth, the distribution of two populations differ only with respect to location parameter. Now, calculation of the Mann Whitney U test formula is given here. You can pause and note down, where U is Mann Whitney U test, N1 sample size 1, N2 sample size 2, Ri, that is rank of the sample size. Use of Mann Whitney U test is used for every field but is frequently used in psychology, healthcare, nursing, business and many other disciplines. For example, in psychology it is used to compare attitude or behavior, etc. In medicine it is used to know the effect of two medicines and whether they are equal or not. It is also used to know whether or not a particular medicine cures the ailment or not. In business, it can be used to know the preferences of different people, and it can be used to see if that changes depending on location. Now, types of question examined using the Mann Whitney U-test here. Good questions answered by Mann Whitney are examining rank differences. For example, did the academic achievement differ by sex, that is male versus female? Does the rank order of university preferences differ by geographic region of student, urban versus rural? Now, to calculate the value of Mann Whitney U-test, formula is given here, where U, that is Mann Whitney, again same thing. Mann Whitney U-test can be used to compare any two data sets that are not normally distributed. Now, steps for performing the Mann Whitney U-test, you can see here. Pause it, collect two samples and sample 1 and sample 2. Take the first observation from the sample 1 and compare it with the observations of sample 2. Count the number of observations in sample 2 that are smaller than and equal to it. For example, 10 observations in sample 2 are smaller than the first observation in sample 1, and 2 equal, then out U statistics for this sample. 10 plus 2 into 1 by 2 equal to 11. Then repeat step 2 for all observations in sample 1 and up all your totals from steps 2 and step 3, rank sum, issue rank sum. Now we calculate the U statistics using following formula. You can pause and note down. Now, where you can denominations here given. What does these all denote? Then example, suppose there is a test performed on the two batches of students and the results are below, batch 1 and batch 2. You can see here, batch 1 and batch 2. Here our null hypothesis will be there is no significant difference between batches. Then alternative, opposite, there is significant difference between batches. Here our level of significance is 0.05. Now we rank the samples according to batches. If two samples have same rank, then we will take the average rank here. This is batch 1, then batch ranks of those batches. Batch 2, ranks of batch 2, rank sum 23, rank sum 55 here. Now we calculate the U statistics with the formula. So our test statistics U are given, that is equal to 2. Now we look into the U statistics table for N1 equal to 6 and N2 equal to 6. And level of significance for the table below, here our critical value is, our null hypothesis will be H0, there is no significant difference between batches. HA, there is a significant difference between batches. Here our level of significance is 0.05. Now we rank the samples according to batches. If two samples have same rank, then we will give the average rank here. This is the table what I was talking about. This is critical value of Mann Whitney U-test here. With this table only, we can decide whether to reject or accept our null hypothesis. Now U0 equal to 5, here U is less than U0, then we reject the null hypothesis. Now Kolmogorov, then Smirnov 2 sample test here. In Mann Whitney U-test, we have tested the hypothesis that the two independent samples come from the populations that are identical with respect to location, whereas Kolmogorov-Smirnov 2 sample test is sensitive to differences of all types that may exist between two distributions, that is location, dispersion, skewness, etc. Therefore, it is referred as a general test. This test was developed by Smirnov. This test also carries the name of because of its similarity to the one sample test Kolmogorov. In Kolmogorov-Smirnov one sample test, the observed sample or empirical cumulative distribution function is compared with the hypothesized cumulative distribution function, whereas in two sample Now let's see what are the assumptions. The assumptions necessary for this test are: number one, the two samples are randomly and independently drawn from their respective populations. 2, the variable under the study is continuous. 3, the measurement scale is at least ordinal. We can see the steps here for this test, KS test. Step 1, rank the data from smallest to largest. Then step 2, computation with the formula. Step 3, again computation with the formula. Step 4, locate the critical value d alpha in the KS critical value table for the specified significance level alpha and the given sample size n. Then step 5, again whether to accept the hypothesis or reject the hypothesis. If you are accepting, if the no difference between, then you have to accept. If there is a difference, then you have to reject. Now 2 sample KS test here, you can pause it and you can understand. The KS test may also be used to test whether two underlying one-dimensional probability distributions differ. In this case, the KS statistic is, a formula is given below, where F1n and F2n1 are the empirical distribution functions of the first and the second sample respectively. Then you have to sum up all the things. Then for large samples, the null hypothesis is rejected at level alpha if calculations or formula is given where everything is donated here, and you can see the graph also, illustration of the 2 sample KS statistics. Red and blue lines are given, each corresponding to an empirical distribution function, and the black arrow is the 2 sample K statistic. You can see here the graph. This one is the KS statistic, the black arrow. You can see here KS test table here, out of which after the calculation we will decide whether to accept or reject the hypothesis. The KS test values are given here, again table. You can see the table for that example. You can pause and see. Now non-parametric tests, goodness of fit tests are given here. You can pause the table and you can check it out. Tests for independence and tests for homogeneity, which tests are used, the table is given. Thanks for your attention and time. If you like the video, please do like, share, subscribe, and I'll come up with the next video in the next upcoming one with the next topic, that is non-parametric tests, that is chi-square. We have done chi-square median test. I will come up with the fundamentals of computers in the next class. Thanks for your attention and time. Happy learning.